in this video, we're going to be taking a look at the June 2015 Physics Regents exam and going through Part A and Part B1, so all the multiple choice. This will probably be split into two videos, so I hope you find this useful in preparing for the Regents. So the first question asks about vectors versus scalars. It says which quantities are scalars? So we have to first think about what a scalar means. It means that it has magnitude but not direction. So velocity and force are both vectors. Distance is a scalar, but acceleration is a vector, so that gets rid of choice 3. And then likewise, momentum is a vector, but power is not, so that gets rid of 4. So speed and work or any type of energy are both scalars. Number 2, it has a mass of 3 kilograms, is thrown vertically upward with an initial speed of 9.8. So we have the initial speed to be 9.8 meters per second, and also too with this video, because just to get the concepts across, I'm going to probably be a little sloppy with my work. So anyway, what is the maximum height? So what do we know about at the maximum height is that we know that it stops. So we're going to call our final velocity 0. Our acceleration is a negative 9.81. And we're looking for that maximum height. Okay, we're looking for that d. So what we can look up in our reference tables, we have the vf squared equals vi squared plus 2ad, and vf is 0. We subtract the vi squared and we divide by 2a. And notice that we have a negative vi squared divided by 2 times the acceleration, so we get a positive distance. If you plug in the numbers, you should get your 4.9 meters. This is a little trigonometry problem. We have a velocity that's going this way, and we have a velocity that's going this way. So we know that our resultant is going to be from the tail of the first vector to the tip of the last one drawn. So we have 220 over here. We have 50 over this side. So these are your two legs. So we could set up a squared plus b squared equals c squared. And we're looking for that side c. So if you do that properly, you get a value of 226. Okay. The next one, we have a 160 kilogram space vehicle is traveling along a straight line at a constant speed of 800 meters per second. So it says the magnitude of the net force. So since it's going at a constant speed, this means the acceleration 0, which a consequence of that we can conclude is that the net force is equal to 0. Okay, so look for the keyword constant speed, net force of 0. A student throws a 5 Newton ball, so that 5 Newton ball is the force of gravity. So if I draw a force diagram at the top, or better yet, really anywhere along that way in its path, we have a force of gravity that's 5 newtons that's going in the downward direction. So choice 3. Number 6, a vertical spring has a spring constant, so we have a K of 100 newtons per meter, and we know it goes from an unstretched length of 0.5 to a stretched length of 0.65, so what we really care about is the difference, the 0.15 meters, and we want to know the magnitude of the weight attached to the object. So the weight, if we draw a force diagram, the force of gravity is going to be equal to the spring force, because when it stretches out fully, it's in an equilibrium state. So if I find the force of the spring, I know that the weight. So if you multiply 0.5 times 100, you get 15 newtons. Number 7, a 1.5 kilogram car is initially moving at 2 meters per second. It's brought to rest by a constant force in 0.3 seconds. So if we kind of write out what we know, I'm going to delete that force diagram there. We know that we have a mass of 1.5 kilograms. We know that it's moving at a velocity, so the initial velocity is 2 meters per second, and we know it stops. Okay, so it's change in velocity. Okay, final minus initial, depending on what direction you choose positive, we're just going to call it a positive 2. And we know the time is equal to 0.3 seconds. So if we set up that your impulse is equal to your change in momentum, we get force times time is equal to mass times change in velocity. Plug in the values that you know. You can so divide by, we're trying to look for the force. Yep. So you divide by time, plug in the values you know, and you will get 10 newtons. What characteristic of a light must increase as the light passes from glass into air? So what we know, I'm just going to delete some things here. What we know is that it is going from an index of refraction, that glass, so the index of refraction is greater than 1, and it's going into an index of refraction of 1. So the index of refraction is going down, and since n is equal to c over v, if n goes down, v goes up. Okay, so if velocity was on here, that would be our final answer. But since it's not, then we have to take a look at the wave equation. Since we know the frequency of the light will stay the same, if velocity goes up, the wavelength will also go up. So choice 4. Okay, this next one, we have a 5 times 10 to the second Newton basketball player jumps from the floor towards the basket. The magnitude of the force of her feet on the floor is 1 times 10 to the third newtons. As she jumps, the magnitude of the force on the floor. This is a nice little third law. Okay, and so you have to be careful of what force are you really looking at, and in this case we're looking at the 1 times 10 to the 3, so the answer is 1 times 10 to the 3, equal and opposite action. The next one, it's a momentum problem, so we know that P equals mv, and we want to end up getting the same momentum for the two objects. Now you could just figure out the momentum and set the second object equal to it, but this is a nice example where you can use some factors and it might be a little easier. So if I look at the 0.06 and the 0.01, I notice the mass is going down by a factor of 6, which in order to keep the momentum the same, the velocity has to go up by a factor of 6. So 6 times the original velocity, 6 times 60, you get 360 meters per second, or choice 3. Number 11 is a force of gravity problem. You're given the weight and you're given the mass, and you're asked to find the gravitational field. So you have the mass of 1.1 times 10 to the third, or excuse me, 1.1 times 10 to the fourth, and you have the weight of 9.1 times 10 to the fourth. And if you divide those two together, you get a G of 8.3. So that's choice 3. The next one is looking at Coulomb's law, okay, where we have the electrostatic force is K Q1 Q2 over R squared. And so you have to ask yourself, what are you changing? And in this case, we're increasing the distance. And since the R is in the denominator, we know that if the R goes up, the force goes down. But it's not going to go down by a factor of 3, it's going to go down by a factor of 3 squared, or 9. So the new force will be 1/9 the original amount. This is just a straightforward plug and chug using Ohm's law. We have V of 3 volts. We have I of 1.8 times 10 to the minus 4. And we know the resistance is equal to V over I. So if you plug those two in, you should get 1.7 times 10 to the 4th ohms. The next one is asking about an electric motor. Motors take electrical energy and create mechanical energy. Think of a little fan or your blender. You're plugging it into the wall, so it's using electrical energy, and it's turning something, creating mechanical energy. So choice 1. The next one is a block sliding across a horizontal tabletop. It comes to rest. Okay, so the fact that it's horizontal is really important because that means that it's not gaining any gravitational potential energy. And it's certainly not gaining any kinetic because it's slowing down, and there's nothing to do with a spring, so there's no elastic potential energy. So the only thing that it could be increasing is internal. You can think about it as the block slides across and slows down, it gets slightly warmer. The next one is based on the definition of an electron volt, although you'll notice that all of your answers are in joules. Be careful when it states an electron. Okay, an electron's meaning that you know the charge. Okay, the charge is equal to -1 elementary charge, or in this case minus 1.6 times 10 to the minus 19 coulombs. And so we have a 3 volt difference, so think of 0 and 3 volts, and we're taking this electron and we're moving it from point A to point B. Okay, and so by doing so, since the definition of potential difference is work over charge, we could rearrange that and say V times Q. So we have 3 volts times 1.6 times 10 to the minus 19, so we get the 4.8 times 10 to the minus Be careful with the electron, okay? If it states the electron or proton, you know its charge and mass. Next one, student finds 6 meters, so we have an L of 6 meters. We have a resistance of 1.3 ohms, and we know that it's copper, so we could look up the resistivity for copper, and I did that 1.72 times 10 to the minus 8. And so we're utilizing R equals rho L over A. And if we solve that around, then A is equal to rho L over R, and plug in the values, you should get your 7.9 times 10 to the minus 8. 18 is the definition of current. It's the rate of charge flow. So we're taking 5 coulombs, and we're dividing it by half a second. Oh, excuse me, 0.05 seconds. 0.05 seconds. So when you divide those two, you get 100, or 1 times 10 to the second. If several resistors are connected in series, okay, so it's a series circuit, and we want to know what is true about the potential difference. Well, since in the series circuit we know that the voltages are all different, and we also know that the currents are the same. So the voltages are different, but the currents are the same. So if the currents are the same, then the only thing that the voltage can depend on is the resistance. And you can see that this is a direct relationship. They're both on the same opposite side of the equation. There's no squares involved. There's no denominator. So we have a classic direct relationship. So it varies directly with resistance, or choice 1. This is a definition of a sound wave. The amplitude is the relates to the loudness. Okay. I will tell you this, that speed and wavelength, okay, if it's in the same material, then these are not changing. 21, duck floats across a lake and oscillates up and down. So we have 5 times, so the number of cycles. So if we think of the definition of frequency, it's the number of cycles per time. So it is 5 divided by 10, or half. So we get half of a hertz, and that's cycles per second. In the 22, we're looking at as the ball falls freely towards the Earth's surface, we know it's going to accelerate. From a dot diagram standpoint, we know that the distance is going to increase, so that's choice 2. 23, a gamma ray and a microwave traveling in a vacuum, so it has the same material. If it has the same material, it'll have the same speed. A student produces a wave in a long spring by vibrating its ends. As the frequency of the vibration is doubled, the wavelength of the spring. So this is related to the wave equation as well, since we know that the velocity, as long as it's staying in the same material, is going to stay the same, that if frequency goes up, wavelength goes down. So in this case, frequency is doubling, so the wavelength will be cut in half. In phase, we need to have some number of wavelengths that separate, some whole number of wavelengths that separate the 2 points. So if we look at point A, if there was an identical part up here, if we look at B, notice B and D are one full wave cycle. Think of a sine graph apart. So there's our answer. So B and D, choice 4. If it said out of phase, or completely out of phase, better yet, then we were going to be looking at 2 points that are half a wavelength apart. So like B and C would be an answer. C and D would be an answer. Actually, A and E would also be completely out of phase, because they're actually 1.5 wavelengths. So it's a half integer multiple of the wavelengths. Okay, 26, longitudinal waves. Key word for longitudinal is parallel. Okay, so longitudinal, the particles vibrate parallel to the direction of the wave. Transverse waves vibrate perpendicular. So if the question asks about transverse waves, the answer would be 2. 27, we have wind blowing across suspended power lines. Anything that has to do with the natural frequency, the driving frequency matching the natural frequency, that's an example of resonance. 28, we have a speaker and a doorway, and the students hearing it, even though they're not in a direct sight of it, and that is because the sound is diffracting through the opening. So that phenomenon we call diffraction. 29, if you look at your reference table and look at the energy in the third energy state for hydrogen, you'll see it's 1.51. So to get up to the ionization energy, that's going up to 0. So the difference between 0 and 1.51 is 1.51. Okay, 30, what is the magnitude of the electrostatic force? This is Coulomb's law. F of E is equal to K Q1 Q2 over R squared. So if you don't know K, look it up in the front of your reference tables. It's 9 e to the ninth. And then if you multiply that by Q1, Q2, and divide it by 2 squared, you should get the 3.6 times 10 to the minus 3. Now, 31 is a nice semi-conceptual, it's like semi-quantitative example. We have two spheres that are touched. Okay, so we know that when they touch, they're going to have an equal amount of charge, not neutral, but equal. And if we look at the net charge, one of them's negative, one's positive, so the net charge between these two is 0.6, negative 0.6 times 10 to the minus 6. So when they touch and separate, they're going to even that amount out. And so if you divide that by 2, you get negative 0.3 times 10 to the minus 6, which is the same as negative 3 times 10 to the minus 7. Okay, so in taking a look at number 32, this is a moving sound source, so think of the Doppler shift. When the sound is approaching you, the wave fronts stack up on each other, so this is a higher frequency, so the frequency goes up. When the wave is moving away from you, the source is moving away from you, this is a lower frequency, so the frequency goes down. So at A, you're going to hear a lower frequency, and the frequency heard at C is higher. Number 33 is asking about which one has the greatest inertia. Inertia is dependent on mass or related to mass, so the one with the most mass is going to have the most inertia. Okay? It doesn't matter the force that's acting on it. All it depends on is the mass. Be careful with number 34. They often ask something along these lines, and you just have to look for the key word, whether it's reflected or refracted. In this case, it's reflected, so the angle of incidence is going to equal the angle of reflection, so choice A is our practical choice. If it did happen to say, so A is the answer, if it did happen to say refracted, then you know that it's going into a higher index, which means that the angle would get smaller, so D would be our logical candidate for that. If the index of refraction got bigger, did I say smaller? So if when it goes in the glass, the index of refraction is going to go up, so the angle is going to get smaller. If the scenario was switched, if this is glass up here, and then we have air down here, the index of refraction would get lower, so the angle would get bigger. So C would be our possible candidate for that case. 35 is a little superposition. Notice that the wave on the right-hand side is larger. So when you draw the superposition, you're basically taking that area and you're subtracting out that area. So what you would do is subtract out this, and what's left is what's above, but it will only be on the line. So what you're looking for is something like that, which is choice 2. Okay, so on to B1, number 36, the diameter of an automobile tire. It's approximately 1 meter, so now you're just looking at things that are approximately 1 meter, and anything raised to 0 power is 1. Here is a little, you could do this one of two ways. You can either use the reference angle given and do something like that, and we're looking for the eastern component, so we're looking for that. Notice that that is opposite the 35, so we're looking at sine of 35 is equal to x over the hypotenuse, which we know is 24, and you could get it from that, or you can use the other reference angle, 55, and the trig function would just be cosine. So either way you slice it, you get 14 meters per second. Number 38, we're looking at if we're including air resistance. So notice that this is something that speaks explicitly about air resistance, so you do want to include it. We know that it's going to go lower, and it's not going to go as far. It's basically going to have drag in both the x and the y direction, meaning it's not going to be able to go as far. So the choice that makes sense or is appropriate to that logic is choice number 4. Number 39, this is just a nice easy problem, but just be careful about the minutes. So the time that you want to use is 120 seconds, 60 times 2. So V bar equals delta D over T. Delta D is equal to V bar times T. So we have 120 times 20, or 1200. Excuse me, 2400. Choice 4. Number 40, a car initially traveling at 15 meters per second accelerates to 25 meters per second. So the change in velocity is 25 minus 15, or 10. And it does so in time of 4 seconds. So if acceleration is change in velocity over time, we have 10 over 4, or 2.5. This one's a little tricky because you're talking about an object in equilibrium, so equilibrium means the F net in both directions is 0. So we can only look at one dimension at a time. So with number 1, that can't balance out. You can't have balanced forces with just one force. 2, you clearly have an unbalance there. 3 is the one that gets interesting because you look at this, it looks like it's balanced in the x direction, but there's nothing on the other side up here to balance out the force in the y. However, with number 4, if you think about it like this, these two forces can be broken up into vectors, and these two can balance each other. And I'll do this in a different color. The two blue arrows can balance out, in theory, the one going down. So the two ups cancel out with the one going down. So this could be an equilibrium, whereas the rest of them could not be. We're looking for the fundamental units for work, and I'm going to look for an equation that has work in it. So it's force times distance. So that means it's a Newton times a meter. I'll put my official unit brackets around here. And you have to then think back of what a Newton is, and that is a kilogram meter per second squared times a meter, official unit brackets there. So this works out to be a kilogram meter squared divided by second squared. Choice 3. In 43, anytime that you're trying to make a graph, don't just try to use your common sense. Find an equation that relates the two variables. In this case, it's potential energy with compression length, okay, the change in length. And notice that this follows the form of y equals x squared, or a squared relationship. Choice 1. 44, this is important just to write down everything you have. We have a power. So the power is 4 times 10 to the second watts. We're looking for time. That's our unknown. We have a mass of 50 kilograms, and it's moving a distance of 8 meters, and we want to know how long it takes. So we know that power is force distance divided by time, so time would be FD over P. But here's the catch, that the force that you're talking about is not the 50, it's the 50 times 9.81. Okay, you're talking about the weight of the object, so that's going to be your force. Plug and chug the numbers, and you should get the 9.8 seconds. 45, a compression toy has launched a 5 kilogram ball. So it's asking for the potential energy, but they give you a mass and a velocity. And so what you know is that the kinetic energy of the object that's moving is going to be equal to, since energy is conserved, to the elastic potential energy that's in the spring toy. So if we find out the kinetic energy, the 1/2 mv squared, then we by default found the PES. And the only thing you got to be careful of is that this is 5 grams, so that is 0.005 kilograms. So that's the m that you want to plug in. If you go through that process, then you end up getting the 0.0625 joules. For the next one, this is an index of refraction. So what we know is that it has a speed of 2.04. So if we look at the index of refraction, n equals c over v, we have 3 times 10 to the 8th at the speed of light in the vacuum divided by the 0.04 times 10 to the 8th meters per second, so 2.04. That's important. And if I just do in my calculator, I get an index of refraction of 1.47. And if I look that up in my reference tables, I have 2 choices. I have both corn oil, which is not listed, or glycerol. So choice 4. The last one here, extend the page for just a moment. We're looking for the energy of photon, so we know that E equals HF, which is equal to HC over lambda. And I'm going to use the second one that I just listed down here because I'm given the wavelength of the 4.8 times 10 to the minus 7. Plug and chug, you get an answer of 4.14 times 10 to the minus 19. All right, and the last page here, we have force versus distance graph, and we're asked for work. So work is force times distance. So I'm multiplying the two axes. By multiplying the two axes, what I really care about is the area. So I have two rectangles. Find the area of one, find the area of the other. I had for the smaller one 3 times 10 to the fourth. For the larger one, 12 times 10 to the fourth. So add the two together, 15 times 10 to the fourth, or 1.5 times 10 to the fifth. Okay, wave A and B, I want to compare them. Notice that wave A takes that long to complete one cycle, so the wavelength would be that far, and then wave B takes that long to complete a cycle, so the wavelength would be that big. But the amplitude for wave A is that, and then the amplitude for wave B is that. So B has a bigger amplitude, shorter wavelength. And if you go through those choices, choice 2 fits the bill. 50, you're looking at the quark composition of a proton. You know that it's composed of ups and downs, or you should know that they're composed of ups and downs because that's what makes up all stable matter. And you know that it needs to be a charge of +1. So if you're looking at the standard model in your reference tables, how can I take an up and a down and make +1? And it turns out to be 2 ups and 1 down. So then if this said for a neutron to get 0 charge, you can do 1 up and 2 downs, and that would make a neutron. So I hope you found this video helpful. I know it was a little longer than some of the other videos that we've created this year. Yeah, hope it helps. Remember that you can, I know I spoke rather quickly. You could always go back, rewind, listen to it again, pause it, think about it, and then move on. All right, thanks for listening. Have a good night. Bye.